Hi everyone! In this lecture, I will continue to solve the systems of linear equations by means of Gauss-Jordan method. And as we all remembered from the previous lectures, we already know what Gaussian elimination method is, what Gauss-Jordan method is, how can we apply these special techniques for solving systems of linear equations, and we also know how to convert an augmented matrix into that of row echelon matrix form or reduced row echelon matrix form, and the elementary three basic elementary row operations that we can use to convert one form of matrix into the other one to reach to an equivalent form of a system. Alright then, and up to this point in this video lecture series, perhaps we remember that we always have had a unique solution for the systems given us. But in this lecture, I will show you the other options that we may run into while we are trying to solve a given system. And as you know, we have actually three different possibilities, right? Only three different possibilities. And the first one is the unique case, which means we have a unique solution. In other words, a unique n-tuple that satisfies both equations in the given system concurrently. However, there are two other options. One is that we can have no solution, right? The solution set could be an empty set, which we showed in the very first lecture, right? In the very first two lectures. And another possibility is that we can also have an infinitely many different solutions, which means the case where we have infinite solution. In other words, our solution set includes infinite number of elements. So, but then one simple question comes to mind. Now, if we have the unique solution, we can simply understand that after we're done with the Gaussian elimination method or Gauss-Jordan method, whatever technique we use, we just start with the very last row and then make our way all the way to the top row and find the values of all the unknown variables. And it is a very simple case, right? It's a very simple computational effort for us to perform. However, how do we understand after applying a Gaussian elimination or Gauss-Jordan method that we have no solution? In other words, the solution set is empty. Or how can we understand that we have infinite number of solutions? Alright then, let's focus on this point and start with an example like this. Suppose we are given the equation x1 plus x2 plus x3 is equal to, say, -1, right? I just make up the values. That doesn't matter. The important thing is to understand what we're trying to show and the logic behind this methods. Alright, and the second equation, let the second equation be 4x2 is equal to, say it 8, sorry, right. Suppose this is a system and we are required to solve this system by using Gauss-Jordan method and abbreviated like G-J. We understand what we're trying to solve, right? Okay, suppose we are given this system, and here's our example, and we are required to solve this system, in other words, to find the solution of this system by using or applying Gauss-Jordan method. Okay, let's start. What is the first step we should take? Well, we need to first represent this given system in the matrix form that is known as augmented matrix form, right? So let's do it. Okay, and how would we do it? We just write down both the coefficients on the left hand side, the coefficients of the unknown variables, which are the coefficients of x1, x2 and x3 in this system, because we have three unknown variables, right? So x1 is one of them, and x2 another one, and x3 another unknown variable, right? So write down their coefficients in the matrix form. This is 1, this is 1 again, this is 1 again, and as we already familiar with this, yes, this dashed or dotted line, and we put -1, which is the right hand side value of the first equation in the system, right? And then for the second equation, the coefficient of x1 is 0. Why? There is no x1 here, right? So actually there is 0 x1, even though it is not here. We know that because 0 multiplied by any value is equal to 0, so this is just cancel out. And there is no x3, right? So we have actually 0 x3 as well here, but you know, since it is multiplied by 0 again, its coefficient is 0, so the coefficient of x3 is also 0, and the coefficient of the unknown variable x2 is 4, and we got 8 on the right hand side of the second equation for this system. Now I turned my given system into its augmented matrix form. Then what am I gonna do after this point? If I am applying Gauss-Jordan technique, then I need to check to see if this matrix is in the reduced row echelon form or not. If it is already in a reduced row echelon form, then there is nothing for me left behind to do. I'll just back substitute and find the solution. But if it is not, then I need to convert this matrix into its equivalent reduced row echelon form. Alright, so let's check it out. So I'm looking first of all to the leading entries, right, of the first row and second row, and the leading entry of the first row is 1 as desired, so there is nothing to do here. And also in the column, which includes the leading entry of the first row, you see the other values besides the leading entry are equal to 0, and there is only one row below the first row. We have two rows, right? It's because we have two equations, and two equations means we have two rows, because each row represents one equation given in the system. And then I just continue to check to see for the second row. I pass to the second row, and what I see here is that the leading entry in the second row is different than 1. So we need to turn this value into value 1. How can I do that? I use the elementary row operation, right? So what can I do? I use the second row elementary operation, which says you can replace a row by a row multiplied by a real value. So if I multiply the second row 1/4 and replace the left hand side row, which is R2, by its equivalent 1/4 R2, then we found this matrix. Let's write it down. We got 1, 1, 1 and -1, and now what we got here, 0, and dividing 4 by 4, right, we got 1 and then 0 and then 2. So now I have 1 as the leading entry for the second row and for the first row as well. But then look at the second column of this newly produced matrix. So in the column of leading entry, all the other values besides the leading entry must be equal to 0, but you know, this value in the first row is not equal to 0, so I need to eliminate this value. In other words, I need to convert it to value 0. How can I do that? Okay, let's do it. So what should I do? Again, continue to convert it into its equivalent form, in other words, reduced row echelon form, what should I do is this. I need to replace row number 1. Okay, so change row number 1 or replace it by what? We add row number 1 minus 1 times row number 2. So why did I just multiply row 2 by minus 1? Because I want to convert this 1 value into 0. And how can I do that? If I multiply the second row by minus 1 and then add it to the row 1, then minus 1 plus 1 is equal to 0 as desired, right? So, and the matrix becomes 1, 0, 1 and minus 3, whereas the second row remains unchanged. I just plug the values as they are, 0, 1, 0, 2, and after each iteration, in other words, after each modifications for the values of the rows, I control my produced matrix to see if it is in reduced row echelon form. And now I have the leading entries 1 in each non-zero row, and in their column, besides these leading entries, all the values are 0 as desired, and it is also in the form of a row echelon matrix, which means that in the first row I have no 0, but in the second row I have strictly more zeros. I have 1 0, right? So the number of leading zeros in the second row is strictly greater than the number of leading zeros in the first row, which means it is in the row echelon form as well. So that's where we stop, right? We're done with the Gauss-Jordan elimination method. We have the desired form of the matrix. Now what should we do? It is time to find the solution set to complete this computational process. And let's see what we got here. Okay, we start at the bottom row, and starting at the bottom row, I know, look at the second row, what we got here. So we said, what was the name of the variables? We got x1, x2 and x3, right? So don't forget them. So based upon the second row, we got 0x1 plus 1x2, which is equal to x2. I don't write 1 again as a coefficient in front of it. So, and I also have 0 times x3 is equal to 2. And these values are cancelled out. They're all zeros, right? So we found the value of unknown variable x2, which is x2 is equal to, right, 2. That's very simple, right? How about x1 and x3? Okay, we move upwards to the first row and write it to see what the values of the unknown variables x1 and x3 are. Okay, so write down x1. Now there is no x2 here because 0 times x2 is equal to 0. I don't write it again. And x1 plus x3 is equal to minus 3. Well, let's look at the situation that we run into. So we know the value of one of the unknown variables, right? We already have found the value of x2, but there is a problem here. The main advantage of this elimination process, either Gaussian elimination or Gauss-Jordan, is to reach to a point where we have at each row one unknown variable. But in this case, x1 plus x3 is equal to minus 3. That means, you know, x1 and x3 could take on any real values that satisfy this equation, right? So I can write, if I move x3 to the other side of the equality, I got x1 is equal to minus x3 minus 3, right? This is possible, or vice versa, or maybe I can move x1 to the other side of the equality, then I get x3 is equal to minus 3 minus x1. So what am I gonna do now? How can I conclude? So we need to make a decision at this point, right? Because we are looking for a solution and we applied Gauss-Jordan method correctly, well, in the best manner, in the quickest manner that we can, but we reached to such a solution. So here you can see that x1 and x3 can take on any real values as long as they satisfy this equality, right? And since there is no restriction on the set of values for these unknown variables, they can take any real value, and the set of real numbers, right, includes infinite number of points, infinite number of elements. So what should I do? Okay, and another thing is that maybe another key observation we should make at this moment, at this very moment, that x1 is a variable and x3 another unknown variable. So I can't just simply write one of them based on with respect to the other one. Okay, so I need to use an additional variable which I call a free variable, and the free variable means a variable that can take on any real value. So suppose x3 is equal to, say it, alpha. Okay, suppose I choose x3 is equal to alpha, and then what it means? What it means is x1 is equal to minus 3 minus alpha. Then therefore now I'm able to write both of these unknown variables with regard to an additional free variable, namely alpha. We can name it whatever we want, say it beta or gamma, doesn't matter. So what is the solution set? So how can we conclude? So the thing is, now the solution is, say it x is equal to, we are looking for a 3 tuple, since we have 3 unknown variables, and x1, x2 and x3 tuple that satisfies both equations in the system at the same time. So, and this is our solution is like minus 3 minus alpha, which is the value of x1, and 2 is the value of x2, and alpha is the value of the third unknown variable x3. And therefore, guys, what is the result here? The result is we have the case where we have infinitely many points or elements that satisfy this system of equations. So what I mean is, alpha can take any real number, right? So alpha is just an arbitrary real value that satisfies this equation. For instance, if I take the value of alpha is equal to 1, then what? Minus 4, and if I plug the value alpha in this 3 tuple, I got minus 4, 2 and 1. This is a solution, right? But if I take the value alpha is equal to 2, then this is another solution. This also satisfies, right? So if I take the value, then minus 5, 2 and 2, and this computational process goes on and on, which means that as the value of alpha changes, the solution set changes, right? And since alpha can take on any real value, which is infinite number, then the solution set also has infinite number of points that satisfies this equation system. Okay, so as long as the difference between the first unknown variable x1 and the last unknown variable x3 is minus 3, in other words, you see, when I sum them up, for instance, if I sum x1 and 3, what I get? You know, I get, that means alpha plus minus 3 plus alpha, and since alphas are cancelled out, we got minus 3. So as long as the sum of x1 and x3 is equal to minus 3, all the possible pairs of x1 and x3s, which is of infinite number, right, satisfy this equation. So just take an arbitrary value of alpha and see that it really satisfies the equations. And to convince yourself, just plug this one of these values in this equation and see that it is satisfied, right? For instance, if we take minus 4, 2 and 1, right? Minus 4, 2 and 1. You see minus 4, right? 2 and 1. As you notice that it satisfies the equation, because 2 plus 1 is 3 and minus 4 plus 3 is minus 1 as desired. It satisfies the first equation, and also it satisfies the second equation, because when you plug the value x2 is 2, then 4 times 2 is equal to 8, right? As long as we choose the x1 and x3 pairs with the property that their sum is equal to minus 3, all possible pairs would satisfy this equation. And this is nothing but saying this system has a solution set of infinite number. So this is the infinite solution case. Well, how do I understand that? After I am done with the elimination process, as we notice, not all the unknown variables coefficients are cancelled out, right? We have something like x1 plus x3 is equal to minus 3 and no other constraint. Okay. Now, well, this is actually an interesting point to notice. And another example, let's see another example to show you another different option that we can run into. Okay, now I will give you another system to solve. Say it, okay, let's make up some equations and values. Say x1 plus x2 is equal to 1 and 3x2 is equal to, say, 6, and x1 minus x2 is equal to, say, 4. Okay, and again, let's try to solve the system by using Gauss-Jordan method. Okay, if there is a solution, and if there is a solution, we need to find it by applying the technique of Gauss-Jordan method. Okay, let's look at the solution. Okay, I represent solution in this abbreviation, like by writing just capital S here. Okay, let's look at the solution. Right, so first step to take is, of course, as always, we transform this system into the matrix form, right? Let's write down, and be careful. Now we have two unknown variables, right? We have two unknown variables, so, but we have three equations, right? We have three equations, so appending the right hand side values as well, then we will have a 3 by 3 matrix, right? We know that, so just be aware of that. I write down the coefficients, and as always I denote the other side by using this line. You don't need to, but I like to use that to indicate that the right hand side are different values. Okay, alright then, and for the second equation, the coefficient of x1 is 0, watch that, and the coefficient of x2 is 3, and the right hand side is 6. And for the third equation, we got 1 and we got -1, right? -1 is the coefficient of the unknown variable x2 in the third equation in the system, and we got 4 here. All right, so this is the augmented matrix form of the system. Then you see the leading entry in the first row is 1. This is as required, and the value right below it is 0, so it is good as well. But this value should be also equal to 0, right? Because in the same column, the values in the same column with the leading entry should all be equal to 0. Besides the leading entry, of course. Leading entry must be 1, but the other values in the same column must be equal to 0. Okay, how can I do that? So I need to eliminate value 1 in the third row, right? The first element in the third row, which is 1. I need to eliminate it, so I need to change its value into 0. How can I do that? And in other words, I need to replace the third row by something else that would enable us to have the desired result. So I add R3 minus 1 times R1, right? If I multiply the first row by -1 and add it to row number 3 and replace it by row 3, then I will find what I want. Okay, so the first row would be the same, no change here because I have not done anything to that. And for the second row, again, we didn't play around with it. Okay, I just write its values as they are. But the third row is now different, right? We have 0 here, and we have -2 here, right? Because I multiply the first row by -1 and adding it to the last row, -1 plus -1 is -2, and -1 plus 4 is equal to 3. Okay, so good. So let's keep doing. Okay, now what we got here? So I'm done with the first row and the first column. So now let's move to the second row, and we observe that the leading entry in the second row is not 1. So first of all, let's change it into 1, and it is very simple to do that. All we need to do is just replacing the row 2 by multiplying row 2 by 1/3, right? 1/3. If we multiply the second row by 1/3 and replace it by row 2, we reach to our goal, right? So just write it again, 1 1 1, right? And now we got 0 1 2 and 0 -2 and 3. All right, so that's good. So let's look at the situation. Well, we got the leading entry 1 right now, but the problem is that it is still not in the reduced row echelon form. Why is that? Because I look at the column of the leading entry of the second row. Second row is a non-zero row, and the leading entry is 1, and I use a different color. If you notice that in this column, besides the leading entry value in the second row, all other values must be equal to 0. So this value should be equal to 0, and this value also should be equal to 0, right? So I need to provide this. How can I do that? All right, let's do it. So what am I going to do is I will continue to convert. So I need to change both row number 1 and row number 3 by something else, right? By applying some legal elementary row operation, and instead of R1, if I write R1 plus minus 1 R2, right? In other words, I multiply the row 2 by minus 1 and add it to the row number 1, which means that the second element in the first row from left to right will be equal to 0. And for the third row, if I add R3 to what this time, because I get minus 2 here, so if I multiply row 2 by 2, then I will find what I need, right? Multiplying row 2 by 2, we got 2 here, and if I add them up, then we got the 0. So let's write our matrix again. Let's write it again, right? What do we get here now? So here's what we get. For the first row, we got 1, 0, and minus 1, and we got 0, 1, 2. We haven't changed anything in the second row in this step. And for the third row, we got what? We got 0, 0, and 7. That's it, right? We got 7 here. Alright guys, we're almost done, but we're still not in the reduced row echelon form. There is something more to do, right? Because now I'm done with the first row and the first column. I'm done with the second row and second column, that's for sure. But I am not yet done with the third row, right? Because the leading entry in the third row is 7, which is different than 1. This value must be equal to 1, and plus, this is not also enough. After doing this change, after making this change, we got 1 here in a simple manner, but then if you notice that there is also minus 1 and 2, which need to be eliminated, right? So first of all, let's change the last row with a simple elementary row operation where we put 1 over 7 times R3 instead of R3. Okay, so now we got 1, 0, minus 1, and 0, 1, 2, and 0, 0, 1. That's good. That's a huge step to take. Okay, now we got the leading entry 1, but we also need to eliminate these values, right? So how can I do that? Again, because it's still not in the reduced row echelon form, right? In the column, these values must be this minus 1 and 2 must be equal to zeros. And then what should I do is that I replace R1 with what? R1, right, plus R3, which is enough, right? If I add the first row and second row, the minus 1 value would be eliminated, and for the row R2, in a similar manner, I replace row number 2 by adding itself to minus 2 times R3, right? If I multiply row number 3 by minus 2 and add it to row 2, I get 0 here. So the final matrix will be this, right? Let's write them. 1, 0, 0, and then 0, 1, 0, and 0, 0, 1. Right. So we are done. with Gauss-Jordan method. Why we're done? That's because look at the last matrix we just found, guys. So now this is actually, you see, the leading entries in, and the leading entries in each row, in each non-zero row, is 1, right? And besides that, also if you look at the columns, right, in each column the only non-zero element or elements are the leading entries of each non-zero row, and all other values in the same column are equal to 0, right? So, and also since this is a square matrix, a 3 by 3 matrix, if I draw the main diagonal, you see that we have an upper triangular matrix right over here. So we have a strictly increasing number of zeros below the main diagonal, which means that it is also in the row echelon form. And in other words, the three conditions of the reduced row echelon matrix form are satisfied. Now we have a matrix which is in the reduced row echelon form, which means that we're done with the Gauss-Jordan method, and we can apply back substitution method to find the solution set if there is one. Okay, now let's go ahead and see what the solution is. Well, one thing that we really focus on in this problem, or we really notice that, you know, look at the last row, and what was our, you know, we have two unknown variables, x1 and x2, and okay, let's plug them back. So based upon the last row, we got 0x1 plus 0x2 is equal to what? Is equal to 1, right? What does this mean? You see, whatever the unknown variables x1 and x2s are, there is some sort of contradiction here, guys, a numerical contradiction. That's because it is nothing but saying on the left hand side we have 0, the numerical value, and on the right hand side of the equality we got 1, and this means that we found a solution like saying, you know, saying 0 is equal to 1, but this is not true, right? This shouldn't be true. In numerical terms, 0 is not equal to 1. This is a contradiction. And even worse, let's go ahead and see. So this is enough to say that there is no solution here, because this equality will never be satisfied, and therefore our solution set is nothing but empty set. So there is no solution here. In other words, there is no single x1 and x2 or infinite number of x1 and x2 tuples satisfying both equations in the system at the same time. So no solution means there is no tuple that satisfies both equations concurrently. So okay, and if you move upwards, you can see a similar thing, like, you know, in the second row, if you look at the second row, we infer that x2 is equal to 0, and with respect to the first row, it means that x1 is equal to 0, which means that x1 is equal to 0 and x2 is equal to 0 is a solution. But is it correct? In other words, if I plug the values x1 and x2 is equal to 0 in this equation, is it true? Right? If I put the values here, 0 and 0, but 0 plus 0 is 0, not 1, right? This is not satisfied either. And again, 0 is not equal to 6. This is not satisfied. None of the equations is satisfied. Okay, so there is no solution. The solution set is empty. Alright, guys. So how can we understand that a solution set is empty, or there is no solution? You see, if we reach to a contradiction like this one that we have just found in this example, then we can simply infer that there is no solution. Yeah, I guess this has been also a very valuable point to notice. In other words, Right, we really made crucial observations. And also in this lecture, well, let's recap. In this lecture, I showed you the other two possibilities where we can have no solution case or infinite number of solution case. And besides that, we also understand how can we make such a decision, right? Based upon what or with respect to what? So after we are done with the elimination process, we just examine through the last row, right, and then the other rows to see what kind of a situation is there for the solution. And also, just because we are given a system of linear equation, that doesn't mean that we will always reach to a unique solution case, right? In these two examples, as we all see, we can also have no solution case or infinite number of solutions. In other words, there can be, in other words, the solution set could be an empty set for a system, or maybe the solution set may include infinite number of elements. Alright guys, that's it for this lecture, and see you in the next lecture, and until then, have fun.